Hello. So if you want to start a project like that or any similar, here are some basics. Uh, First, you want to collect the data about what you want to achieve. This small project goal was to make a six-axis robot able to lift a bottle of beer or anything else to this wave. You could also know how far you want to pick and place material, but I didn't have any special needs. Uh, So the dimensions of the robot are kind of random in this case. Uh, Mostly they are from the dimensions of the gearboxes. I, and I was only able to change length of the arm between the motor 2 and 3. Just I made it to look good. Mm. So my data is 1 kilogram weight of a full bottle. Then first thing you want to do is draw your wave. It can be a block or make it look kind of better, like here by drawing a real bottle. That helps you to check if there will be no collisions while moving. So, um, uh, so now the next problem is how big should be the motor and the gearbox. In my case, I had few of NEMA 17 motors. They are cheap, so good choice for the small project like this. I had to know what is the torque of the motor. On sites, they write about holding torque of the motor. This is not a real torque we are looking for. Mm, As you can see, the random first one, uh, holding torque of this one is 1.68 Newton meters. So real torque is kind of smaller than this. It's like 10% or something like that. Mm. Easiest way to check how much torque your motor have is to make some make a gearbox with torque like 49 to 1 I have. So 7 times 7. Uh, and after you connect the motor, here I have servo, which I was testing, but you would want to make a plate able to connect with any other motor like NEMA 17 and NEMA 23. You want to check how much force it will take while moving. Here are some wave discs. I think that each one was 2 kilograms, but I had space to add some more or less. The length from the axis to axis, I think it was 200 centimeters. Yeah, about 200 centimeters. Millimeters, sorry, 200 millimeters. So I was able to counter from this move. Uh, the worst that can happen while the motor is moving, that where you have a wave, your like robot arm, going down and suddenly stopping 90 degrees from the ground. So we're looking for the value, how much it can lift and not drop uh, after the suddenly stop or the direction change. Uh, Slowly, as you will be adding some wave, it will be going down, stopping normally, or moving up and down. You're testing the no ramp for the motor, so it's suddenly starts, suddenly stops. You want to check the full force as I'm like now using in my project. So after adding some more and more kilograms, when it was going down and stopping, it just dropped down to the bottom because it lost the steps of the stepper. So I was looking for this value and made some calculations. As for my smaller NEMA 17 motor, I had torque 0.06 Newton meters The bigger one, NEMA 17, is 0.12, and for NEMA 23 was 0.28. But your values could be, I think, bigger because I couldn't check very precise how much it was. Because I was able to only change the discs like 1 kilogram. I didn't have any 500 grams or 200 grams, so it's not very precise, but it works. I know it will lift anything from these calculations. Mm. After we know the torque of the motor, we can go back to the drawing. So always you start from the item you want to lift. Do not start to draw any machine from the backside, from the first part. The first part is always the what you want to lift and how. So the first calculations for the axis 6. So this is axis 6. It is not needed to have huge torque, as I assumed it will be holding stuff close to the center axis. So I use only 25 ratio planetary gearbox, 2 steps. If I could, I would use less, but ratio 5 is not very strong with the smaller NEMA 17 and could not hold after change of the mass center. Counting mostly begins when checking needs for axis 5. So now we have some length and mass from axis 6 and our bottle. Inventor can show us the mass center of this part. It is very important to update I properties of every printed part, as it's never we will never use 100 fill. Usually it's from 20 to 50%. So weight of every part after print is very important because it will be like according to the program very heavy, and it's really not. So now if I check the from the axis for the 5 axis to the mass center, it's 96 millimeters. And I will check the weight. Weight of this one is like 2 kilograms. And when we put it to the calculations, I have 0.06 for the smaller motor, and here we have calculations, so the arm, mass, and what I need to ratio of the gearbox. So my arm is 0.1 meters, like 10 centimeters, and mass is 2 kilograms. So I need at least 32 ratio. So going back to the drawing. So here I have hidden the motor with planetary gearbox, but I could fit only ratio of 25 and I need 32. Had to do it by belt, so I printed another part, just a wheel pulley to make another ratio of 2. So totally giving me ratio of value 50. So it should hold steady this mass. So for the assembly tips, it's very important to hold every bearing with a screw if you can. So very good visualization is like here, I think. Yes. So I use bearings, and those are normal screws. Those not for the bearings, but good enough. Here I have bearing held by small screws. I think screws M3. Yes, M3 screw. My gears are 7 millimeters, mostly because of the bearing. I think I couldn't fit I needed some room, and yeah, I couldn't make it smaller, because if you end the material here, this bearing could go outside from it. I had this problem in one of the axes. I think one time it broke. I didn't know why. I had to disassemble everything, and I found out that here those gears are very small, so I'm not able to hold them by screws. This is M4 screws, no place for M3, even M2. Nothing will help. So this is designed to have to soldering station, and this is additional material which I am heating up, and it's slowly going down to the bearing, so it won't come loose and go out. The problem was that here those bearings went straight to the wall and blocked themselves on because of couldn't spin of the because of the friction. So from one side you hold it by the small wall, and other side you can hit and melt the material down. It's like very important to do it like this. Of course, between stages, always bearing to hold the like all the axes together. This is axis 3, and no, it's axis 4. And so 3 bearings just to hold everything in the line. So because of that, when I had 2 bearings, it was moving too much, I think. So, of course, try to make everything smallest you can. Maybe you don't need so thick gears. Maybe use some smaller bearings, or like friction bearings. You can always like make some small changes, just to not only make it cheaper but also lighter. As for the printing tips, you should try to calibrate your printer so that you won't have to change dimensions for bearings. If you have bearing with 50 millimeters outer diameter in project, should be 50 millimeters, and after print bearings should go into body without huge external force. You should be able to click it inside using just your hand. So I So like this diameters should be exactly like the bearing, and it really should go inside without any huge force, and also you don't want it to be loose. Uh, it's kind of important, because in the past I was using some press to fill to push bearings inside, and after I wanted to disassemble it, it was really hard to get it out. Mm. So as for the gear, uh, how to make a planetary gear without losing too much material. First, you would like to make is print a slice of the planetary. So you print like 5 millimeters thick external gear, planetary gears, and internal gear. Not more than 5 millimeters, because you want to check only if they fit together, and it will be like moving a bit at least. So you will don't change the external, the outer uh, gear, internal gear. Try to always change the planetary gears or the middle one. So do not scale it. You don't want to scale the gears because you will lose this the diameter, yes? After scaling, you won't be able to fit bearing inside. Rather, make a something like this. You make a. I want to have a smaller gear, so I just take the outer. I change it not very much. You should use 0.05 or 0.1 is maximum, and then just get rid of the material. So it will be a bit smaller. Then you print it and check if it's fitting well. Uh, I think that's the best we could do. I made so many tests, so it's very good way to do it. Mm. As for the design tips, uh, so general designing tips, you know that every motor and sensor, like servo here, everything has cables. So don't forget to make some place to get the cables out. Mostly people mm, like do not remember about this, but here I had to make a hole. So from this motor inside here, no, which I kind of lost. From this motor, I have cables coming out here. They are going inside the hole through this, avoiding the end stop. They connect with those wires here and go out here to the next stage. The next stage motor is hidden inside. Also have like cables coming out here, going inside. They connect with those that were before, going to the next step. And here we have from both sides, coming from the motor and proximity sensor, going into the shell. Mm. So it's like huge amount of space inside just for the cables to like zip them together. And together they go out through here to the next step and inside. Oh, not very well. Oh. They have a middle hole from the both sides, like the upper one. From the motor and proximity, they are coming inside, and those through the main axis. So I couldn't make a planetary gearbox set watching in line because of the bearings would not those gears would not allow to go cables through. So this is like for another movie, uh, how these last steps look like and the different types of bearings. Those are the actual bearings and standard huge bearings just to hold it together, but not no time to tell about everything now. Uh, so when there's not so much calculations as you see, just remember to collect the real torque of the motor, not what they write on the side, because never true. Uh, there are huge differences between one NEMA and other 17, even if they are almost the same dimensions. So, Okay, and thank you for listening.